Okay, guys, did you miss me? Well, I missed you, and now we're at the point of calculating mixtures. We now know how to directly calculate separately a strong acid, separately a weak acid, or a polyprotic acid or a polyprotic base. Now we're going to look at a mixture. If we're going to calculate two strong acids together, a strong acid and a weak acid and a weak. Now, in a way, some of this type of calculation is similar to the polyprotics, though with a little bit of an extra switch to it, and that is dilution, because when I say mixture, it means I am taking one pot or one beaker which has a strong acid and a particular volume with another beaker which has a weak base and a particular volume. Okay, so there's an added bit that is a little bit different than the polyprotics. Mixtures of bases, we're going to also look at strong plus strong base plus a weak base, and a weak base with a weak base. Okay? I'm going to take one recording to do that, but also we're also going to then, within the same bit about mixtures, we're also going to talk about mixtures of two or more acid-base couples. So I have mixtures of two or more acid-base couples where there is possibly some reaction between the acid and the base couples. In other words, reactions which is not just with water. And yes, the calculations here does vary greatly from anything that you've seen above, and thus I'm going to discuss it completely in a separate section with its calculation. Okay. Now, I would have also preferred to discuss buffers since they are mixtures in this area, but I've decided just to completely put it separately because there's a lot of problem sets and its style of thinking and its equation does differ on its own. Okay, so mixtures of two strong acids, get to the point directly. Both acids will contribute to the H3O plus concentration, and yes, then the pH will be minus log of the H3O plus total. Well, sounds very easy. Well, it is. But what I have to do is I have to calculate this H3O plus total. And no, it's not just the addition of whatever the initial concentration of this acid is plus the initial concentration of that acid is, because we have a dilution, because I have a mixture. And so for each of the concentration of H3O plus from the first acid, let's say, that's the concentration of that acid initially times a volume that it had divided by a new total volume of the mixture, thus the dilution, plus the concentration of the second acid times its volume of the second acid divided by the total volume of the mixture. And so that way we would get the concentration of each H3O plus that has now already been diluted in solution. And literally, it's like here, concentration times volume, that's just number of moles. So it's calculating the number of moles of H3O plus coming from the first acid, plus the number of moles of H3O plus concentration times volume of the second acid divided by the total volume. Right. Very direct question. So HCl, 50 milliliters of it, and its concentration is 0.05 moles, is been added to 150 milliliters of 0.1 molar a nitric acid. And you all know already that HCl and nitric acid are both strong acids, and therefore you're going to, this is a mixture of two strong acids. Now here we want the pH and we want the concentration of all species in solution. So directly to the point, H3O plus will be what? Concentration of the first acid times the volume plus concentration of the second acid times the volume divided by the total volume. Okay, so make sure you do all the upper part together and then divide by the total volume. Notice I kept the volumes in milliliters, and the reason is because it's a ratio, so the milliliters eventually cancels out. You don't have to convert it to liters. And the concentration of H3O plus total comes out to be a number 0.088. Of course, you can do the calculation of pH, which is simply minus log of that number, which comes out to be 1.1 pH value. Now, if I want the concentration of all species, of course, I didn't do this here, but you can calculate the OH minus coming from the autoionization of water. You have H3O plus, get the OH minus. We can also get the Cl minus on its own because that just comes from the first dissociation of the strong acid, HCl. So that's going to be 50 mils times the concentration, 0.05, but divided by 200. Why 200? Because even if I just have the Cl minus, the total volume of solution is 200. So that gives me its concentration, and the nitric acid will be the concentration of the nitrite will be the concentration of nitric acid, 0.1, times the volume of that acid, 150, divided by total volume. That gives me the number of moles of the NO3 minus. There isn't an example in your textbook about mixtures of two strong acids. You can see why it's too simple. Okay. Now we're going to look at when I have a strong acid mixed with a weak acid. You already have seen something like this when we talked about H2SO4, because that was a strong acid in the first dissociation and then a weak acid in the second dissociation. And you should have solved a problem where we looked at that in the problem set. Now, regardless, both when we have mixtures of acids, whether strong or weak, again, don't forget that both of these are donors of H+, so there's no reaction with each other. Both of them will react with water. If the Ka of the weak acid is low, that means I could simply say that my H3O plus in solution is mainly going to come from the strong acid, and then the amount coming from the weak acid is literally negligible. And so my pH will be mainly determined by the concentration of the strong acid. Okay, so minus log the concentration of the strong acid, but I have to make sure now that the concentration of that acid is diluted due to the mixture. So you take first the concentration of that strong acid, and you get the new diluted concentration, which is the initial times the volume of the strong acid divided by the total volume, which is volume of the strong plus volume of the weak acid. So get the strong acid concentration in the solution after dilution, and simply get the pH as minus log of that concentration of strong acid. There is an exceptional case, and actually the only case is really H2SO4, where the Ka of the second acid is fairly high. Okay, the Ka is fairly high, and something like 10 to the minus 2 value, and that is when I have to consider both the strong and the weak acid in my calculation of H3O plus in solution. And the way we did that is we simply used the second acid dissociation or the weaker acid dissociation. So you take the weak acid dissociation and you put as a concentration of H plus the concentration of the strong acid, whatever it is. Okay? Pretty much like what we did as a calculation of the strong acid H2SO4. And I want you to re-look at that. And then we use the Ka equilibrium to get the amount of H3O plus that will come from the weak acid dissociation, because it is affected by the presence of the strong acid dissociation. Once you do the calculation of H2SO4, that example becomes fairly simple. A mixture of two weak acids, okay? So we have two weak acid, a weak acid HA with a concentration C1 with a K value, Ka value for the HA, we call it Ka1. Now, watch out here. I don't mean that this is a diprotic acid or a polyprotic. It just means that we call it Ka1 for simplicity. Okay? HA2, the second acid, has a concentration C2 and a Ka2 value for its Ka. Now, of course, very reasonably, if the Ka of the stronger acid, HA1 per se, is greater than 100 Ka of the weaker one, then this amounts to a simple monoprotic calculation, and we don't, or even a single acid calculation, as if I don't have a mixture at all. This is very similar to the calculation type that we did with triprotics or diprotics, where we simply had a single equation taking place. But in that case, it wasn't a mixture, remember, it was just a normal one solution, one species or one acid, which happens to be triprotic in a solution, but there is no dilution fact. Here, however, we have to consider the dilution. Okay, so let's say we considered only the first equation to calculate H3O plus, because now the second equation is negligible for H3O plus calculation. But we have to watch out for dilution. What does that mean? That means if indeed that the concentration of this acid HA1 is greater than 100 Ka, what concentration am I looking at? I'm looking at the diluted concentration. So you have to do a dilution first for this concentration. Get the new, which is the old concentration initial times the volume divided by total volume of solution. Then ask yourself, is this diluted concentration greater than 100 Ka? And this is, we call the Ka1. And if it is, then indeed you could use pH equals half pKa1 minus half log C. Final, in other words, diluted form. Of course, if that concentration is less than 100 Ka, you have to go back and do a quadratic. And the quadratic comes simply from the Ka of the first acid there. We still don't consider the second acid. What about if the two Ka values are close? That, in other words, none of them, neither one of them is 100 more than the other. And actually, when they are close to each other, then we have to consider that the H3O plus comes from both acids, but both acids also have become diluted. In order to get an equation for this, we actually have to look at the electroneutrality of the solution. That's the easiest way to get this type of calculation of a pH. We consider that the autoionization of water is negligible, thus my OH minus in solution is also considered negligible in the electroneutrality expression. Let's look at the electroneutrality expression, which is right here. Again, electroneutrality, positives on one side, negatives on the other. Let's look at the positives. We have H3O plus coming from the acid, from this one, from that one, maybe from water, whatever. All the H3O plus, we only have one cation on this side. The negatives will go on the other side. A minus 1 and A minus 2 go on this side, plus the OH from the water. Again, we said that the OH from the water is negligible. And so actually what I'm allowed to do is simply kind of say that this is negligible, so I could remove him in solution. And that amounts to equation here. Once I've removed the OH minus, that means H3O plus is only these two A minuses. And what do I do here? I convert each of these A minus into some expression which has only concentration, and H3O+. Okay, now, How do I do that? Go back to the Ka. Let's look at the Ka of this first equation. Remember, Ka of this first equation will be products divided by reactants. So H3O plus times A minus divided by HA1. If I solve for A1 minus, A1 minus becomes Ka times HA1 concentration at equilibrium divided by H3O plus at equilibrium. If I consider that the amount dissociated AX is negligible, and in other words, that the amount of this reaction just doesn't proceed greatly, that means that the concentration of HA1 in solution is simply at equilibrium, is simply equal to its initial concentration in the solution, which is actually the diluted form. Likewise, let's look at the second equation. Ka2 for this one will be products divided by reactants, okay? And solve now for A2 minus. And in the same reasoning, we consider that X is negligible, that the HA2 concentration is at equilibrium is simply equal to its concentration in solution without dissociation further. And so once we substitute that back in and we solve for H3O plus, we multiply H3O plus here multiply the whole equation by H3O plus, we get H3O plus squared is this expression. So H3O plus equals the square root of Ka1 C1 plus Ka2 C2. Guys, I talked about all this. It mounts down to this equation in yellow. H3O plus, don't you remember something like this, equals square root Ka1 times C, or Ka times C? Yes, that is just monoprotic calculation of H3O plus. And of course we did that first, and then we get the take minus log of both sides and you get half pKa1 minus half log C. This is the same exact thing. So remember the square root Ka times concentration plus another Ka times another concentration because we have another acid. So you just need to memorize this bit, okay? This is mixtures of two weak acids. But, and a big but, and all of you end up making this mistake, and I don't know why. Do not put the initial concentration here. This is the concentration after dilution, okay? So the C1 here is the concentration of the acid after dilution. The C2 is the concentration of the second acid after dilution. Okay. Here they've really simplified things a bit with this type of question, and it's the same type of question number 38 that you're going to be homework, that is going to be homework for you. I don't like it because it just tells me the following. I have a mixture of 0.1 nitric acid, cyanic acid HCN, they gave me a Ka, and 0.1 nitrous acid HNO2. Well, of course, neither of these acids is strong, which you already know, and they gave you a Ka value, so it's automatically both are weak. And they want a pH. Well, what I don't like about this question is they don't give me volumes. That means it's like I have a mixture and they didn't really tell me this is the amount of acid that I added inside this mixture, which forces me to make the following conclusion or the following assumption, and that the concentrations given here in the question are the concentrations after mixing, okay? So these are the concentrations after mixing, okay? So if you're not given volume, you assume that the concentration given is after mixing. I don't really need the species in solution. Of course, you have three acids, if you will, or three equations that take place. The acid dissociation of HCN, the acid dissociation of nitric acid, and of course, autoionization of water. We assume autoionization of water is neglected. That's automatic by weak acids, done. We look at, is the Ka of the nitrous acid greater than 100 Ka of the HCN? And voila, it is. look at this Ka, it's way greater than this one, and therefore we can assume that we only have a single weak acid in the solution that contributes to the H3O plus concentration. Once I have that, so I only have one, really as if one acid, one weak acid, to calculate pH, that is. So what do I do? What is this acid? It's a weak acid. Is its concentration greater than 100 Ka? What concentration? The concentration after dilution. Well, in this case, it's the same. It's 0.1 because we assumed that this is a concentration. Is that greater than 100 Ka? If it is, great, then the pH equals half pKa minus half the concentration of that acid, again after dilution, and it happens to be the same, 0.1. Substitute pKa, substitute the concentration 0.1, and solve for pH. Okay, and the last slide on this first recording of this section is calculation of mixtures of weak bases, okay? I have two bases, a B1 and a B2, and it happens to be a neutral type of base, kind of like the ammonia. Okay, so here's a neutral base, so when he picks up a proton, he becomes positively charged. Okay, so BH1 plus and OH minus is released in solution. I have two bases with a concentration C1 and KB1 and a concentration C2 and a KB2, two different bases. Of course, just like we did with acids, is the concentration of, can we neglect one of them? And you ask yourself, if I can neglect one of them, I really simplify things. So is one of the KBs greater than 100, the other KB? If it is, then you neglect the contribution, let's say, of the weaker base, the KB2 in this case, we neglect him. And so all of the calculation of OH minus will come from the first equation only, but don't forget dilution. And so first you did the concentration of the stronger of the two bases, get its concentration after dilution, check if it's greater than 100 KB. If it is, then simply put POH equals half pKb minus half log concentration of that base. Of course, if it's less than 100 KB, use a quadratic equation. The quadratic comes from that first equation. However, if the two KB values you cannot neglect one of them such that neither one is 100 times greater than the other, or that these two KB values are close enough to each other, then both of them will contribute to the OH minus, and don't forget to dilute both acids in these calculations. We also get the expression here for the calculation of OH minus in the solution, and thus pH from the electroneutrality principle. Let's look at the electroneutrality equation in this case. Well, here's my equations. I have OH minus negative on one side, and I have positive on the other side, positive HB1 plus, HB2 plus, and don't forget the H3O plus from the autoionization of water, which contributes both H plus and OH minus into solution. But we're going to neglect autoionization of water, so H3O plus is negligible, and we get an expression. And this expression is again under the conditions where the concentration B in solution at equilibrium is equal to its initial concentration in solution because the amount dissociated is negligible. In other words, X is negligible, okay? Is negligible. In other words, the concentration is greater than 100 KB1 for these types of calculation. Again, OH minus amounts to the HB1 plus and the HB2 plus. For each of these species, get the species from the KB expression. So the HB1 plus from the KB expression, So go get KB will be HB plus times OH minus divided by B1. Solve for HB plus. HB plus will be KB1 times B1 divided by OH minus. But B1 is simply the initial concentration of that base in solution, in other words, diluted concentration, because X is negligible. And thus, the calculation of OH minus in solution of mixtures of two bases where neither one can be removed is going to be, that looks so familiar, square root KB times C plus KB2 times C2. Oh, that's exactly what we did with calculation almost of the acids. Instead of H plus, I have OH minus. Instead of Ka, it's Kb. So it's easy enough for me to memorize this expression. Once I have OH, of course, you're going to get POH, and then you get pH. But please, again, don't forget that these concentrations are the diluted concentrations in the solution. Okay, and that's it. All right. There isn't much problem sets to solve here, and I'm going to move on directly to the next recording, and because this is going to be too long, about mixtures.